Yeah, thank you for the introduction. So I'm Tzung-Han. So today I will talk about a different approach compared to the previous talk. So we are focusing on about functional programming and high-level synthesis and with routable and programmable hardware. So our target is FPGA devices. So you may ask why FPGA? So you can see we have several accelerators like CPU, GPU, FPGA, ASIC. But for ASIC and FPGA, it's typically very efficient, especially for the power consumption, because we can customize the hardware architecture inside that. But another problem for ASIC and FPGA is they are difficult to program compared to CPU or GPU, because especially for ASIC, it's a fixed architecture, and for FPGA, you need to write the HDL first to configure the FPGA. So that's a problem we want to handle now. So because FPGA is low power, low bandwidth, and it's hard to program. So basically, this is the problem we want to solve: how to program. So let's look at the example here. So we have the element sum for 2 arrays, and this is a Python code. So this is very simple, right? We just get each element from 2 arrays one by one and sum them together. But how do we do the same thing in HDL? So this is another example. So you can see it's verbose. So we need to talk about, okay, we have a clock and we need to count the number with a register, and then we need to handle the handshaking protocol. So it's much more complex. So that's a reason HDL is more difficult to program, and people want to use high-level synthesis to generate the code instead of writing the low-level language. So a very typical method is HLS, especially for C-based. So there are several tools like Xilinx and Intel's tools. But these kind of tools, they can provide very simple program like this. So you can see this is a C++ example for vector addition. So, but the problem is if you fit this into their compiler directly, you will get a hardware that performance is pretty bad. That is because we need to optimize them manually. So what kind of optimization we will do is something like, okay, we need to insert the programmer to say, okay, we want pipeline here, we want to unload here. But all these things are related to hardware architecture, so it's very low level. And another problem is usually it's very difficult to guess what's happening at the hardware level, because the tool, it works like a black box, so you have no control. You cannot predict the performance very accurately. And that's one of the reasons we want to go with functional approach. So this is the previous tool, as mentioned in another talk before. So we have several kind of primitives like map, reduce, and basically is to apply a function. For example, map, so apply a function to a sequence of input, and we have zip to group 2 arrays together one by one. And at this level, we don't have the information about hardware implementation. So the later stage, what we will do is we will, for example, for map, we will load it to a new IR system, and then it has more information about hardware, like, okay, data comes in a streaming way. So in the hardware, we know exactly clock cycle 0, we process the first element, clock cycle 1, we process the second element. And it probably is not good enough if we want it to be finished very fast, so we probably can further parallelize it. So we have another version like map vector. So it's basically, okay, we create several instances of function and then process it all at the same time. So we know at time 0, we just process all at once. And this is the compiler step we have. So it's also for previous work. So we have something for very algorithmic to express the algorithm only. So we don't have hardware details. So we basically use the same example for array sum. So sorry, for vector sum addition. So basically we group 2 arrays together, 1D array together, and then do element addition one by one. And then we will load and optimize the code, and then we get a more parallelized version. And with this, we exactly know what's happening at the hardware. So we know this clock cycle, what's happening, another clock cycle, a certain thing is happening. So that's easier for us to do cost modeling or some kind of optimization. But this is just the start of the story. So the real problem is if we have an application like neural networks, how do we fit into a device like FPGA? So this is an example for VGG16. And we will start with something simple like, okay, we look at 3 layers of land, and these 3 layers are exactly in the same shape. And we now have a device, FPGA device. And FPGA device usually it has a limited amount of resources, and multiplier is the most expensive one. So as long as we have this amount of multipliers, and we want to feed these 3 layers into the device, then what will happen? So the most naive way is, okay, we probably reserve a certain multipliers for 1 layer. So for this example, we reserve most of the resources for layer 1, but we will run out of resources for layer 2 because we just exclude these multipliers for a certain layer. So that's not what we want. And a more ideal approach is, okay, right now we can see all these layers are less and they use the same amount of multiplication. So why don't we just share them across all the layers together to actually we can squeeze these 3 layers into a single device. So this is what's going on in the prior world. So the prior world, they are using that binding to share a function and then use function code to handle each function's assets. So this is the example. So we have a function is declared at the beginning. So it's basically turn a string with an element as the input, and then output is a string of an element as well. So we have a share function f, and then usually the data comes from memory interface. So what we'll do is, and we want to call this function several times. So what will happen? So the first thing is we will have an address. We will get the address for the read data and the writing target for another address. So T1 is our writing target. So basically what we are doing is we will combine map string with read to read the data 1 by 1, and then we will combine reduce and write to write the data 1 by 1 back to the memory. And then in the middle we have the function code, and it just grabs the data from one source and then process it and then store the data to the destination. So this is the first function call. And if we want to call it multiple times, it will be something like this. So we want to use the data from T1, and the partial ratio from T1 is saved to the destination T2. So you can see we read T1 again, and then do another function call and save to T2. And then we will do the same thing for the third function call and save the final result to out. So this looks simple, but what's happening in the hardware is it will be more complex, and it's the problem from the previous work. So we will talk about what will actually happen in the chip. So we have a share function and memory interface, and then we have initial data in the memory. So for the first function call, what is happening in the chip is we will allocate the space or the resources. And these resources including this path, this blue line, and then the block that function call 1, and then the reduce and map and read. All these things will occupy a space on the chip. So you can see there's a problem, because if we have multiple function calls, so it will occupy another space, and a third function call will occupy another space. So you can see it's actually scale with the number of function calls we have. And if we have something that, okay, ResNet 50, it has 50 layers, so it means we have 50 function calls, so we definitely cannot fit into device. Then how to solve this problem? So we definitely cannot go with the model with function call style. So right now we switch to a primitive, actually just seen. So it's reduce. So because reduce, usually people use that to do array sum to accumulate element 1 by 1, like this one. So basically we take an aggregation function, and it as one of input, another input is the streaming data. So right now what we want to do here is we still target at the same function, and then we want to make this reduce to iterate over different things. So it's actually the memory address we have. So like this, right now we read the memory, base memory from the memory space, and then it actually has two parts. One is the read address, one is the write address. So we read this, and it will become a string of 3 elements, and each element contains read and write at the same time, and we will iterate over this to model the function code. So we will see what's happening later. So right now we have a reduce, and it actually accepts this instruction as the input, and then it will iterate over that. And the things here is we will need to figure out what's inside. So because basically we have a function, and then this function will accept the input read from the memory and write, and it has a write primitive to write the data back. And then these two things, read and write, you will accept the base address from the memory. So it it's similar to the instruction in CPU, but for each instruction, it will take actually several thousand cycles to process because you know the target is convolution, fully connected layer, or something similar. So based with this, you can see the architecture inside the chip is much concise compared to the previous one. So we can actually make things more compact. But another problem is right now we only talk about these 3 layers are the same, but how about we want to handle 2 layers? They have different shapes. So if we look at the IR or the primitives we have, you can see if a function takes a string as the input, it has size n. It means it must all the time it must take size n. For example, 100, size 100, it must take a string of 100 all the time. It cannot take a string of 10, a string of 20, and the output is a string of 100 as well. So it's not flexible. So it also happens to the primitive like map string. So it must take a string with a fixed number. It cannot be changed. So right now, if we have 2 inputs, that the string with size 28 and the string with size 14, so it means we must to determine the size right now. If we choose the large one, it means we need to somehow reshape the small one, like padding, we make it larger. But it means we waste the computation because these padding 14 values are actually doing nothing. And if we choose the small one, 14, as the final size, it means we need to somehow tile the larger one. But both of these are not efficient at the hardware because it means you need to create some extra components to handle the shape. So what we want to do is to introduce a new type. So right now we only have a string main type. It must handle a fixed size string. And then right now we have something new. It's called upper bounding string. So it means we just give it an upper bound, but the real string size will be determined at runtime. So it means if we determine an upper bound string with 100 elements, it means when you really run a program, it can be something between 1 to 100. So, and this is something we want to introduce to handle the issue of different shapes. So let's go back to the similar example. So right now we just make it a little bit harder. So right now you can see the function. It takes n as a string with size is as an input and output. The output shape is string with size n minus 1. So right now you can see we start to make the shape a little bit different. So what we will do first is, right now because we have this new type, so we can actually make instruction more flexible. So first we allocate space to tell us, how many instructions we want to have. So in this example, we put 3, but actually you can put 1. So you will just do one command at a time. And then what we want to do is, we have a reduce, and you can see the reduce is and the map. There are new version. There are reduce upper bounding string and map upper bounding string. And what we have right now in the memory is, we still have our base address, but right now we will have the new thing because this length we still have not determined the length. So at the next step, we will fill the function. We will call the function and then feed the data from read and write the data with write. But both of them, it takes the base address, but the problem size is changed. So we also have something new. It's called uCounter. So it's an upper bounding string counter, and you will set a number from runtime and this is actually the final length it will produce. Yeah. So it means sometimes we can produce n minus n size n. Sometimes we can produce n minus 1. And then you can see here in the instruction encoding, we need to include this information as well. But this helps us to handle, right now we have several convolution layers. The shapes, they are actually different. And then we fix another problem for the shape, and now we still have a problem because neural network, they can have several types of layers. So in this simple example, we still have one more layer is fully connected layer, because the handle convolution layer, handle fully connected layer might be different. The optimization target will be might not be the same. So how do we handle this? So let's look at so this is something from the previous slide. So we have this architecture, we have one single function there, but right now we want to introduce a new function. So we have function 1 and function 2. So how do we handle this? And we use a new primitive called switch apply. It's similar to switch, but it takes a pool of functions. and then an input with certain type, and then we have a selection signal to say, okay, which function we want to go with. And with this, we can introduce a new function. So we have function 2 and function 1, and then just wrap them out with switch apply. So switch apply now takes two function f1, f2, and then we have selection signal. So you can see here in the instruction we have a opcode. So opcode is basically okay determine which branch we want to go with. So with this we can make the accelerator to handle more than two problems at a time. And this is basically our approach. So we will show you an example about how is this expression looks like in our real test case. So we want to show you the net 5 is because it's simple, it's not too long. So basically we want to write the data back to somewhere else in the memory. So we have this write address. And for the neural network, usually we have several layers and we want to fuse that together. Like convolution layer is followed by rewrite, quantization, pooling. So the next layer for example, we have a pooling there, and you can see we have a switch apply here to say, okay, we want to go with identity, do nothing, or just do pooling. And you can expect the shape are different, but thanks for our upper boundary string type, then we can actually merge them together without problem. And then we have bias and quantization. So basically, it means we need to read something for bias address and then control the quantization bit width. And then we have the main computation. So it's basically, okay, we have, because you know convolution and the fully connected layer, they can be decomposed into such a dot product. So we have a dot product unit, and then partial sum and then to do partial sum if the layer is too large, we need to somehow tile that. And then we have the component to read the address to read the data for image and wave for convolution, and the same for the fully connected layer. And then you can see we somehow twist the read address generator for convolution and fully connected layer is because their shape are quite different. So we need to do something more. Okay. And then we evaluate our approach on Area 10 FPGA. So we first show you the previous work. So in previous work, what they are doing is they use the net-based sharing and use function code. So what they are trying to do is, okay, they have the convolutional VGG16, and then they synthesize it with a certain amount of DSP. DSP is a number of parallel multiplication we can allow, and GAPS is the performance number, and peak routing is the maximum routing congestion inside a chip. So you can see if they don't use they do not use too much DSP, it's routable, it can be synthesized. But if they use too many, like more than 1,000, the peak routing congestion is over 100, so it's not synthesizable. But with our approach, we can actually synthesize that with the same amount of DSP. Of course, we sacrifice something because you know we need to read the instruction first, so we have sacrificed something too, and the performance is to be lower. Okay, and for okay, I will go. And for Tiny YOLO, and another example is Tiny YOLO. For Tiny YOLO, we actually get a better performances because Tiny YOLO has a larger input size. It means each layer may have quite different sizes, and because we introduced upper boundary string, it means we can handle different shape more properly. And the next one is ResNet 50. So this is a large example we have, and we compare against a prior. We just want to show, okay, we can perform better than somebody also use Area 10, and then you can see if we use different number of DSP, the maximum number of routing is not changed too much. So it means our approach is kind of scalable. And the next thing we talk in our title is programmability, because we mentioned that. So sorry, you already overshoot. Okay, sorry. Okay, yeah. So what we have is we have an accelerator, and it can support two different type of neural networks at a time, like VGG16 and VGG11. So I will jump this, and then yeah, for convolution. So conclusion, we have reduce upper boundary string and switch apply to put things together to make things programmable and routable. And then this architecture is not new, but our contribution is to express this behavior with functional IR. And that's all. Thank you. Yeah.
Thank you. Okay, and it's even a comment I have to make, not a question. So you have put in a lot of interesting work on handling these streams, but you have been mapping them to FPGAs.
Yeah.
I wonder, why have you not used devices that support these streams natively, like Xilinx's or AMD these days, Versal FPGAs, which have this array of 400 VLIW AI engines with hardwired streams between them? So I think this would be a brilliant programming approach for such a system, and it would be far more efficient than targeting FPGAs. You can run these AIEs at over 1 gigahertz.
Yeah, so this is also a problem we're facing before, is because we need to compare against different systems. For example, the system you mentioned is, I think it's suitable for this problem, and then yeah, because we start our work with FPGA, so we work with them, and we are also considering to extend them, but it needs time. So right now we are thinking about, okay, we have our Intel device, we are switching to Xilinx device, but we are still working on something that, because their interfaces are different, so we need some other work to do that. So that's the reason we don't talk about this here. Yeah,
Thank you.
But that's a very interesting point. Yeah.